Hi everyone, this is Isha. I'm one of your TAs for 213, and I'm going to be doing a midterm 2 review for your test coming up. Just as a brief overview of what I'll be doing, I'm going to give you a quick review of fundamentals, things that you'll want to know for the test, and then I'll go over some example problems. I do have everything written out already instead of writing out the examples as I go because I just find it to be quicker, and also I write really messy when I try to write and talk at the same time. But what I will do is post the PDFs of these notes onto the Canvas as well. So if you ever have trouble following along, you can just look at the PDFs as a reference. You can also, pause the video or whatever. Okay, so your midterm is going to be over 2 topics overall. We're going to be going over torsion and then bending, and so I want to review a couple of these key concepts really quick. So torsion, in the instances that we're talking about for this class, is the twisting of a circular shaft. You don't need to worry about any instances of stuff that's non-circular, although it is possible that you'll get a hollow shaft. So a couple of terms. Torque is represented as T here. It's a moment that twists the shaft, and so because it's a moment, its units are going to be Newton meters, in pound inches, etc. You have angle of twist, which is represented by phi. Its units are going to be radians or degrees. And phi is a measure of the twist caused by torque. You've got torsional shear stress, which is represented as tau, because its stress is going to be in pascals or psi or some variation thereof, so like megapascals or kilopascals, stuff like that. Tau is the stress that is caused by a twist on a shaft. And then you've got polar moment of inertia, which is J, and that's essentially a measure of how much a shaft resists twisting. So the units for a polar moment of inertia are going to be meters to the fourth, inches to the fourth, etc. So the 2 equations for polar moment of inertia that you're going to need to know are polar moment of inertia of a solid shaft here, and then for a hollow shaft here. The only difference between the 2 is that here for a solid shaft you've just got the 1 diameter, and for a hollow shaft, you have your outer diameter and your inner diameter, and those both play into the equations. Alright, and so all of these factors that we just talked about go into the torsion formula right here, which is a formula for stress. And so the formula is tau is TR over J, stress is torque times the radius over J, the polar moment of inertia. And so you might see this formula with a couple different letters in the place of R. R can be replaced with rho. It means the same thing, it's just the radius at which you're measuring the stress. And you might also see the equation with a C. This is specifically used for the tau max equation because C is indicating that the radius is the distance to the outside of the shaft. So basically you're using the biggest radius you can, because when your radius is to the outside of the shaft, it's when your stress is the biggest. And so tau max might be seen as TC over J instead of TR over J. Alright, our next formula is the angle of twist formula, and that is phi, the angle of twist, is equal to TL over JG. T is torque, L is the length of the shaft that is being twisted, J is your polar moment of inertia again, and G is your shear modulus. This is a material property. It's usually pretty big, like in the scale of gigapascals. And if you remember Young's modulus from before when we were doing normal stress, it's a similar type of value. Just remember that this is a material property. You usually will not need to find it. It should be given to you in most cases. Also keep in mind that the angle of twist formula gives you radians. So if you're looking for degrees, you're going to have to convert from radians to degrees. Alright, and then very last thing on torsion is that just like we had statically indeterminate problems on the last test for like deflection and stuff, you can also have statically indeterminate torsion. And that usually comes in one of 2 forms. The first one is when you have a bar that's being twisted, but it's fixed on both ends. And so the way you express that, your compatibility equation is going to look something like this. So we know that because it's fixed on both ends at A and C, our angle of twist between A and C has to equal 0. And then you can take your phi AC and break that down into parts. And so we can say, I know that the angle of twist from A to B plus the twist from B to C has to equal 0 because I know that the angle of twist from A to C is equal to 0. The other statically indeterminate problem you might see is something where you have like a compound bar, maybe something on the inside, a material that's different from the outside. And that's not what it's supposed to look like. Cool. And so in this case, basically your equation is just going to be that the angle of twist of the outside has to equal the angle of twist on the inside because they're like laminated together or whatever. So for this case, I have maybe a core of steel, outside is aluminum, then I know my angle of twist of steel has to equal my angle of twist of aluminum. So these are the two statically indeterminate problem types that you are likely to see if you get a statically indeterminate problem. And remember that when you have indeterminate problems, you first take your equilibrium equations from any supports, and then the second equation that you add is one of these, is an equilibrium equation, which helps you solve for all of the variables you need. All right, going on to bending. So the big thing with bending that we've been spending a lot of time on is shear moment diagrams. So always remember the first thing that you do with a shear moment diagram is find the support reactions. And basically all you need to know is that a pin can't hold a moment, but it can hold forces. And if you're fixed to a wall, if you have a fixed support, it will hold a moment if it has one. So keep that in mind. After you find your support reactions, you can use either method of sections or the graphical method. So method of sections is what you're going to remember from before, where we have like a beam, and then you can make cuts at all the different locations where there's maybe a torque acting on it, and you're going to evaluate your reactions at the cut. So like if I have a cut here, 1, then I might draw this portion. I'll include this torque, and then I'll have my reaction forces here, maybe a moment, and a shear force. This is a way to make shear moment diagrams, but it generally takes a lot of time because if you have a lot of different forces acting on a beam, you're going to have to take a cut every time there's a force. That means a lot of integration generally. It generally takes a lot of time. On the test, I would definitely be familiar with how to use the graphical method because it is a lot faster. And there are quite a lot of examples of graphical and of method of sections posted in the different professors' notes. So if you're still confused on how to make shear moment diagrams, I really recommend looking at examples. I think the easiest way to figure out how to do shear moment diagrams is just by looking at a bunch of examples of how they're done. And then you use your shear moment diagram. Step 3 is usually to find like your maximum moment or maybe some other kind of value you derive from the graph. This is kind of an aside. On the graphical method, I just want to review really quickly. The way the graphical method works is that your W, which is the magnitude of your distributed force, is equal to the slope of your V. So your shear diagram is based off of any distributed loads that you have. That also means that a change in V, a change in shear, is equal to the area under a distributed load. So if you have, for example, a rectangular load and you can calculate the area of that rectangular distributed load, you can use that information to draw your shear diagram. Similarly, your shear is equal to the slope of your moment, and so that means a change in your moment is equal to the area under your shear. So again, if your shear is like a triangle and you can calculate that area, you can use that information to determine what your change in moment is. This is really important and also really confusing. Your sign convention for the graphical method is a little bit different from what you have like learned in the past and what you've been using in the past. So the first two are pretty straightforward. For W, for your distributed load, up is positive. So if you have a distributed load that is pointing down, it's going to be negative. For your shear forces, any point forces that point up are positive. Here's the confusing one. For moments, clockwise is positive, not counterclockwise. This means you can't use the right-hand rule. You have to keep in mind that it's basically the opposite of the right-hand rule. I know it's confusing. I also understand that like technically sign conventions are basically like fake and don't really exist, but for our purposes, the reason we care about this sign convention in particular is because this helps the graphical method match what we get using the method of sections. So this is really, really important. Try to keep this in mind. I know it's confusing. The way that I like to think of it is, okay, like if you have a moment that's an external moment acting on your beam, and you're drawing a shear moment diagram, your shear moment diagram is the reactions of the beam to your outside forces. So if you have a clockwise moment acting on the beam, you're going to have a counterclockwise moment reacting to that. And so basically what I'm saying is, like, if it helps to rationalize in your head the fact that the reason clockwise is positive is because you're comparing external to internal loads. If that helps you, that's one way to remember it. But yeah, basically just, this is confusing, but point moments that are externally acting on your beam, clockwise is positive. All right, moving on. For bending stress, let's go over a couple definitions. For bending moment, M, that's a moment that bends the beam. The units for that are going to be Newton meters or pound force, inches, stuff like that. Your neutral axis, which is NA, is an axis where stress and strain both equal 0. If you have a symmetrical shape like an I-beam or a rectangle or a circle, your neutral axis is just going to be straight down the middle. If it's not symmetrical, you can locate the neutral axis using the geometric centroid. And the equation for a centroid is right here. Y bar is equal to the sum of all of the intermediate centroids, so the centroids of all the subcomponents, times the area of all the subcomponents divided by the area of all the subcomponents added together. And we'll have an example of this later if that doesn't make sense to you. Your distance y is your perpendicular distance from the neutral axis to the point that you're trying to evaluate. So sometimes you're not trying to evaluate the moment at the surface, but maybe like in the middle, or like at some arbitrary point. So your distance y allows you to adjust where you're evaluating your bending moment. And then you have your moment of inertia, which is a little bit similar to your polar moment of inertia. But in this case, instead of J, it's I, and it's a measure of how much the beam resists bending. Your units are going to be meters to the fourth, inches to the fourth, that kind of thing. 3 important equations for moment of inertia. The moment of inertia of a rectangle is the base times the height cubed divided by 12. For a circle, it's pi times the diameter to the fourth divided by 64. You don't have to know how to derive these, just know that these equations exist and be able to apply them. And then if you have some like weird complicated, so for example an I-beam or a T that doesn't fit into one of these 2 cases, what you can do is you can find the moment of inertia of a compound, and the way you do that is you take the sum of all of the subcomponent moment of inertias plus the area of each subcomponent times the distance squared that it lies from the neutral axis. And this is another one that we'll have an example of later because I know it's a little bit confusing in this form. All right, last thing is our bending stress formula, and that's sigma b, our bending stress, is equal to the negative moment times the y, which is the perpendicular distance from the neutral axis, divided by the moment of inertia. Similar to the other equation we talked about before, the tau for torsion, sometimes y can be a different letter, sometimes it's c. Specifically, c is used for sigma max, for the maximum stress, because once again, when you're furthest from the neutral axis, your stress is the greatest. And so c is the furthest distance from the neutral axis, and that's used for calculating maximum stress. The other thing to keep in mind with maximum stress is that sometimes they'll take the absolute value of it, because once you've found the bending stress, maybe they don't care whether it's tension or compression. So that's just something to keep in mind. All right, that's an overview of content. I know that was kind of quick. I'll post the PDF. Don't worry if you feel like you missed something. All right, let's do a couple torsion examples. And these are problems out of the book, so this problem is just taken out of, I think it's the 10th edition. All right, so we've got a steel shaft made from 2 segments. AC has a diameter of 0.5 inches here, and then CB has a diameter of 1 inch here. And so there's a thicker and a thinner portion, but the whole thing is solid and it's all made out of steel. So if the shaft is fixed at both ends at A and B, but it is taking a torque in the middle, determine the maximum shear stress in the shaft. So ultimately what I'm looking for is the maximum shear stress. That tells me I'm using that tau equation we talked about. But the fact that it's fixed at both ends tells me that it's statically indeterminate. And so there's a very set way that you deal with statically indeterminate problems. So what we're going to do first is equilibrium. And so what I've done here is I've just redrawn this figure here from like a straight on 2D side view, just because it's a little more straightforward. And I've replaced these fixed supports with torsion at A and with torque at A and torque at B. So the reason I've drawn them in this direction is because I only have one torque acting on the whole shaft, and it's this 500 pound-feet. I used my right hand rule to figure out that it's pointing to the right. So if you wrap your hand around, it's going around the shaft this way, you figure out that my 500 pound-feet is acting to the right. Because that's the only torque that's acting on the shaft, my reaction torques are both going to point to the left. So my equilibrium equation comes from the sum of moments is equal to 0. 500 minus TA minus TB is equal to 0. So this is my first important equation. My second important equation is a compatibility equation. And so this is what we talked about earlier. Because the problem is statically indeterminate, I have to come up with a different relationship that helps describe the shaft so I can basically deal with all the variables. So in this case, I know that point A and point B are fixed, so my angle of twist between points A and B has to equal 0. I'm going to break phi AB down into parts, and so I'm going to say my twist from A to C plus my twist from C to D plus my twist from D to B has to equal 0. And then I'm going to apply this equation that I showed you earlier, the phi is equal to TL over JG. That's my angle of twist equation, and I'm going to apply that to each of these individual phi's, and I'm going to get 3 terms in this equation that I'm going to use for the rest of the problem. So what you can see that I've done here, I've plugged in TAC, LAC, and JAC for my phi AC, but because the whole bar is steel, my G value, which is a material property, is going to be the same for all of the values. So in reality, you could just cross these out here because they're going to be all the same value and it equals to 0 at the end. I do that a little bit later, but if you want to get it out of the way, you're welcome to. Okay, so now we're going to come over here to the left, and I'm going to find my TAC, TCD, and TDB values so I can plug them in over here later. And the way I'm going to do that is just by taking cuts at each of the locations where there's a difference, where there's a torque acting. So first I have a cut 1 here between A and C. And basically I throw away everything to the right of my cut. I draw my reaction torque, which is going to be TAC because it's section AC of the bar. My sum of moments equation tells me that TAC is equal to TA. And now I have cut 2, which is between C and D. And you can see actually that my moment equation gives me the same result, that TCD is equal to TA. In reality, you really don't need to do cuts 1 and 2. You could get away with just doing 1. That's because there's no torque acting in between cuts 1 and 2. The reason I've done both kind of is just to make it really straightforward so everyone is on the same page. But in reality, if you wanted to skip a step, I mean, feel free to. And then our cut 3 here gives me TDB is equal to TA minus 500. If you want to throw away the left side of the cut instead of the right side of the cut, you can also do that. You would end up with something that looked like this, with a cut here. Oh gosh. With a cut here, and you would have your TB, and then you would draw your TDB, and you would just say that TDB is equal to negative TB. I've kept the left side instead and written it this way because I want to keep everything in terms of TA. That will help me solve the equation a little bit more simply later on. Okay, so now I have values for TAC, TCD, and TDB. I'm going to take these values and plug them in over here on the right. In addition, I've also plugged in the other values that I know. So my length AC is 5 inches here, and then my length CD is 8 and 12. I've kept G of steel, my shear modulus, just symbolically there, but I'd cancel it out in the next step. And then what I've done here is I've substituted in the dimensions that I know into my polar moment of inertia. And so that's really the reason I had to separate section AC from section CD, is not because they're experiencing different torques, but because their shaft diameter is different, so their J value is going to be different. And what that means is I have to do it in 2 terms instead of just 1 in order to preserve the fact that AC is thinner than CD. And so you'll notice that my J value here is different from my J value here. Okay, so plug in everything you know, cancel out all the numbers you don't need because they're all the same. You do a little bit of algebra, you can figure out from here that TA is equal to 60 pound-feet. And then we can pull this equilibrium equation that we found up above down to here and use that to solve for TB, and we get that TB is equal to 440 pound-feet. So we've used the first 2 steps of the indeterminate process, so the last thing we have to do is, because the problem is asking us to determine the maximum shear stress, let's do that. So we know the shear stress equation is tau is equal to TR over J. And I'm going to apply this in 2 different places. I'm going to apply it at TAC and at TDB. And the reason I'm not doing it for CD is because, like we talked about earlier, the torque that acts on AC is the same as the torque that acts on CD. But because AC is a lot thinner, it's going to experience more stress. That's because when you have a force acting on an area, when the area is smaller, the stress is greater. And so because I have the same torque acting on this whole thing, but AC is thinner than CD, I can know for sure that the stress in AC is going to be bigger than the stress in CD. So because I'm only looking for the maximum shear stress, I'm just going to ignore CD. I don't even need to calculate it. I am going to check, though, dB. The reason I'm going to check that is because my torque, my TB is really, really big. And so I want to make sure that that's not the location where there is maximum shear stress. So I'm going to check in those 2 locations. I know my TAC value, I know my diameter, and I know my J value from what I plugged in before. So basically what you're going to do is calculate the stress in those 2 segments. You're looking for maximum shear stress. So between these 2 numbers, TAC is slightly bigger. So ultimately, come on. We're going to say that this is our maximum shear stress, is that TAC is equal to 29.3 KSI. All right, that's problem 1. Let's do another torsion example. Grab some water. All right, this problem 5.92 in the book is that you've got a shaft subjected to a uniform distributed torque. T is equal to 20 kilonewton meters per meter. Once again, your job is to determine the maximum shear stress developed in the shaft. Like before, it's fixed at both ends. That tells you immediately that it's a statically indeterminate problem. So we're going to follow basically the same process as we used before. So what I've done, one other thing to notice, your cross section here is that your shaft is actually hollow. It's all one material, but it's hollow in the middle, and that's going to be important later when we calculate the moment of inertia. Okay, so I've done what I did on the last problem and just done like a straight on 2D view. Honestly, I'm not exactly sure how to draw a distributed torque, so I just did that. I hope it's pretty clear that it's just a torque that's acting over the section of AB. And like before, we only have one torque acting, so I'm just going to assume that my support reactions are in the opposite direction. So I have torque at A and torque at C, which are reacting to my distributed torque. So the first thing we do is an equilibrium equation, sum of moments, and I've done the same thing I did before, TA plus TC, and then I'm subtracting the magnitude of the torque, 20 times 10 to the third, times the the length that it's acting on, which is 0.4 meters. That gives me my first equilibrium equation, and then for my second equilibrium equation, I need a compatibility equation. Like before, I can say that the angle of twist from A to C is equal to 0, but I can't do what I did in the last problem because instead of point moments externally, we have a distributed moment. And that means we can't make cuts because you can't really cut in the middle of a distributed load without doing a bunch of algebra to help you figure out what the value is. So instead, we're going to use the method of superposition. So you probably remember this from deflection, where you can like separate out the forces that are acting on a beam into the individual components and then add up all the resulting deflections in order to find the overall deflection. You can do the exact same thing with angle of twist. And so what we're going to do is, here's our overall beam. We're going to break it down into the angle of twist, which results from just the distributed torque. Add to that the angle of twist that results just from TC, the torque at C, because those are the two torques that are acting on the shaft if we pretend it's fixed on one end. And so here are the 2D like side representations of that. You've got your distributed torque but no TC, plus no distributed load but a TC over here. And so we're going to use these in order to find our two angles of twist. So first, we're going to find our angle of twist due to small t, our distributed load. You're going to do this as an integral because it's a distributed load. So it's essentially the same as the equation TL over JG, but instead of using L, I'm integrating over x. And so I have t in terms of x dx over JG. I'm integrating that from 0 to 0.4 because that's the area that the distributed torque is acting on. So first thing I'm doing is I'm pulling JG out of the integral because it's a constant. So I have 1 over JG, integral from 0 to 0.4, and then I have the value of what my Tx is. So my Tx is the distributed load value, negative 20 times 10 to the third, multiplied by the distance that it's acting on, x. And the reason it's negative is because if you use the right-hand rule, it's pointing to the left. Then we've got a dx on the end. Next, I'm pulling this constant out of the integral. So I have negative 20 times 10 to the third over jg times the integral from 0 to 0.4 of x dx. And if you plug in all those values, ultimately you're going to get that the angle of twist due to the distributed load is negative 1600 over jg. We're going to do the same thing for the second part of our method of superposition, where we just have the torque acting on the end. So we have angle of twist due to TC is equal to TC length of the whole beam over JG. So the length of the whole beam is 1 meter. So we're going to plug that in. We get that angle of twist due to TC is equal to TC over JG. So now we're going to pull this equation from the top down here and plug in those values that we just found. So negative 1600 over JG plus TC over JG is equal to 0. So we can do what we did before. We know that because there's just one cross section for the whole thing, we can cancel out J. And because the whole thing is made of the same material, we can cancel out G. And what that leaves us with is that TC is equal to 1600 Newton meters. Now we can pull down the equilibrium equation, this one up here, and use that to find TA is equal to 6400 Newton meters. Now the last thing we have to do, once we have all this information, is to calculate the stress. We're going to do the same thing that we did in the last problem, where we use tau is equal to TR over J. And I have written here that the maximum stress is at A. And let me explain why I'm not calculating the stress at all the different points. Because now I know my values of TA and TC. So TA is 6400 Newton meters and TC is only 1600. And in addition, right here, the shaft is experiencing opposing torques. So you have TA, which is really, really strong, which is going to the right, and then I have my distributed load, which is going to the left. And so this point right here, where it's experiencing both of those torques, is going to be the area where they have maximum shear stress. So in a situation like this, where it's very clear what area is going to have the maximum shear stress, you don't have to waste your time calculating the shear stress for all of the different cross sections and then saying, okay, this number is the most. If you can clearly deduct and explain why a certain area is going to have the maximum torque and thus the maximum torsion, you can just go ahead and use that specific point. So in this case, my maximum stress is going to be at A. So tau A is equal to TA times R over J. In this case, because we have this hollow shaft, R is going to be the maximum distance from the center of the shaft out to the outside. And so in this case, that's my outer diameter, 0.08 meters divided by 2. That's 0.04. And then for my J, my polar moment of inertia, I have pi over 32, and then outer diameter to the fourth minus inner diameter to the fourth. If I plug all those values in, I get that TA is equal to 93.13 megapascals. I also wouldn't worry too much if your shear stress values are pretty large. Stress tends to be in the order of kilopascals and megapascals. I mean, like, I'm not going to guarantee that for sure, but like, don't worry if your numbers are really big, because sometimes stress is just a very large number. Okay, let's move on to bending. So this is problem 6.81 from the book. You've got a beam that has some kind of material, and they're telling you that it has an allowable tensile stress of 125 megapascals and allowable compressive stress of 150 megapascals. And they want you to determine the maximum moment, M, that can be applied to the beam. So this is an allowable stress problem, but first of all, what we want to do is deal with the geometry of this beam because it's not really standard. So the first thing I'm going to notice is that because it's not symmetrical about this axis, I can't just say that the neutral axis is in the middle. And so what we're going to have to do instead is to find the neutral axis. And this process, I would think of it a little bit like finding a weighted average. It helps you find where the neutral axis is, where there's no stress acting on the cross section of the beam, by finding the geometric centroid. So what we're going to do is we're going to measure all from the bottom, like right here, this red line. This is my reference point for all of my measurements. So I'm going to find y bar, my neutral axis, by taking the sum of all of the intermediate parts. So I've broken the t into two different parts, and I'm going to find the y bar and the area for each of them and plug them into this equation. So here you can see I've started with this blue bar here. So my y bar is 0.015 because it's this dotted black line. It's 0.03 divided by 2 because it's the distance from my reference line, this red line, up to the centroid of my rectangle, my blue rectangle. I'm multiplying that by the area of the blue rectangle. Same thing for this pink rectangle over here, except I'm measuring from this bottom line up to the centroid of my pink rectangle. And so that's going to be 0.3 divided by 2, so half of this vertical line, plus all of 0.03, all of the height of that blue rectangle. You're going to multiply that by the area of the rectangle, and then divide by the area of the blue rectangle plus the area of the pink rectangle. When you do all of that math, it comes out to 0.0975. So then what you can do is, if you've drawn a relatively two-scale cross-section, you can look at what roughly 0.0975 looks like, and does that seem like a reasonable answer for where your weighted average neutral axis would be. So in this case, it looks about right. The bottom has a big rectangle on it, so it is going to pull the neutral axis towards the bottom. So once we have our neutral axis, we can find our moment of inertia. And we're going to do this with a very similar process. We know what the moment of inertia of a rectangle is. And so all I have to do is add up the two separate rectangles in a special way in order to find the moment of inertia of the whole cross section. So the way I'm doing that is I'm breaking it down into rectangles, again, the same two that I did before. I have my moment of inertia of that given rectangle. So here it's BH cubed over 12. My base is 0.3. My height is 0.03. I'm adding to that my area of the rectangle multiplied by the distance from the neutral axis, here, my overall neutral axis, to the centroid of my rectangle. So it's this distance right here. And so in this case, that distance is going to be 0.0975 minus 0.03 divided by 2. I'm going to do the same thing for my pink rectangle here, finding I, my moment of inertia, which is base times height cubed over 12, adding the area times the distance squared. In this case, it's going to be my distance from my neutral axis here up to the centroid of my pink rectangle. And so that value is going to be 0.18 minus 0.0975, because 0.18 is the total distance from here to that red line. All right, once you plug all those values in, you get your I, which is 1.907 times 10 to the negative 4. Similarly to how I would tell you don't worry too much if stress is a really big number, don't worry too much if your moment of inertia is a really small number. Because you've got all these cubes and squares and stuff, the numbers can get really magnified very quickly. So if you've got small values like this, don't worry too much. All right, now that we have all that information, we can finally find our bending stress. So we have our allowable bending stress equation. It's sigma is equal to my over I. Because the problem wants us to find moment, I'm going to rewrite that equation in terms of m. So m is equal to sigma I over y. And then the next thing we need to do is figure out where tension is happening and where compression is happening. And so what you can see in this beam is that you've got this moment which is kind of curving upwards. And so basically what that means is the direction that the moment is curving towards, that part of the beam is going to get pressed together and compressed, while the other side of the beam is pulled apart so that it can stretch and make it bigger. And so if I was looking at this beam from the side and I had my moment acting like this, it would deform and turn into this. And what that means, if I've got my moment acting here, is that this is in tension and this is in compression. And so what that means on this cross section here is that up here I've got compression and down here I've got tension. That's important because it tells me what numbers I plug in where. So we're going to start at the bottom. We know that the bottom is in tension, and so I'm going to use the value here that's given to me for tension, which is that allowable stress for tension is 125 megapascals. So I'm going to plug that into this equation. Moment is equal to allowable tensile stress here, 125, multiplied by y, which is the distance from the neutral axis to the bottom, which is 0.0975, divided by I for the whole beam. I'm going to get a value for the moment here. I'm going to do the same thing for the top, which is in compression, but I'm going to use the different allowable stress value that's given to me for compression. And then here, my distance, y, is from the neutral axis to the top of the T instead of the bottom. And so you can see that's the total height, which is 0.33, minus the height that goes from the bottom to the neutral axis here. So 0.33 minus 0.0975. And then I'm going to plug in my same I values before. I get a different MC value. And so the question is asking me, what is the biggest moment I can apply to the beam that's within these allowable stresses? And so between the moment due to tension and the moment that gives compression, I know that my maximum allowable moment is going to be the smaller of the two numbers, because that's the maximum value that is going to be allowed with the stresses that I was given. So the maximum moment that can be applied to the beam is 123 kilonewton meters. All right, last problem. This is another bending problem. This is 6-88 from the book. And you've got this compound beam. It's pinned together here at B. And they're asking you to determine the absolute maximum bending stress in the beam. Both of the segments have the same rectangular cross-section where the base is 4 inches and the height is 12 inches. So because the cross-section is a simple rectangle, I know the equation for the moment of inertia of a rectangle. It's symmetrical, so I can just say that my neutral axis is down the middle. So I don't need to do a lot of that calculation that I did in the last problem. Instead, what I'm going to do is I'm just going to start by finding all of my reaction forces. So here at my fixed end, I have a reaction in the x direction, a force in the y direction, and then a moment. And then here at C, at my roller, I have just a force in the y direction. But because it's a compound beam, it's pinned together here, I'm going to have to separate it into two parts in order to solve for the reaction forces. So what I'm going to do is I'm going to split at the pin B. I'm going to look at BC first on the right. And what I get from that is when I split at the pin B, I get a reaction By. In reality, I would also have a reaction Bx here, but we know that that equals 0. So I have a moment equation and a sum of forces. Based on that, I can find my Cy and my By values. Using that, I'm going to look at the other side of the beam, part AB. And remember from statics, when you have something that you've separated at a pin, if I found By to be positive here, I assumed it was positive. I'm going to have to assume it's negative here in order to balance it out. And so based on that, I have another sum of forces and another sum of moments, and I use that to calculate all of my values, basically. So now I have all of my reactions. Now I can go into the actual part of the equation that I'm trying to solve. So what I'm going to do is I'm going to draw a shear moment diagram. The reason I know I need a shear moment diagram is essentially because it's asking me for maximum bending. I know I need to find the maximum moment, and the way you find the maximum moment is by making a shear moment diagram. So I've used the graphical method here. If you want to use the method of sections, unless the instructions are specifically telling you not to, like, you're welcome to use it, it just will take a very long time. So let me explain kind of what my process is going on over here on the left. So I have a distributed load. It's pointing down, which means that it's a negative distributed load. And so what that tells me is that my shear moment diagram is going to have a negative slope. So here, because your distributed load is a line, it's basically a 0 order. That means that my shear is going to become a first order, a line, and then my moment is going to become a second order, or a parabola. So this is like 0, x, and x squared. And that goes back into that relationship we talked about earlier, where each of these is, so it's basically like if you took the moment diagram, you took the derivative, you would get the shear diagram. If you took the derivative of the shear diagram, you would get the distributed load diagram. The other thing to keep in mind is that anywhere that there's an external force, you're going to have a jump in your shear force diagram. Anywhere there's an external moment, you're going to have a jump in your moment diagram. So what I really should have drawn here that I didn't, that I will really quick, Cy, Ay, and I had a moment A. So these are my external forces and external moments that are acting on the beam that are going to cause jumps. So knowing that information, what we're going to do is we're going to look at our shear diagram. So I start at 0 here, but because I have Ay acting at A, I'm going to immediately jump the value of Ay. So Ay was positive 26, so I'm going to jump up to 26. Now from A to B, I have this negative distributed load, and that tells me I'm going to have a negative slope. The distributed load is 2, so my slope is going to be negative 2, so I draw a line with a slope of negative 2 all the way to B. And now I can use another trick that I know, which is that the change in V is equal to the area under W. So if I can find the area under W, which is 2 times 9, which is 18, I know that's the amount that I lost from V. So I started at 26, I lost 18, so I end with 8. At the end of my distributed load, I only have 8 left. And now from here, from B to where the 12 kips is acting, there is nothing going on in the beam. So when there's nothing going on in the beam, my shear force doesn't change, so it stays constant until here, where I have a point load. And so we talked about how external forces cause jumps in your shear diagram, and so this external force of negative 12 kips is pointing down, negative 12, is going to cause a jump of negative 12 in my shear. So if I went from 8 minus 12, I get a negative 4 value here, and then again from this negative 12 kips all the way to the end, there's nothing going on. So my shear force is going to be constant. And then here at the very end, I have Cy, which is equal to 4, and that's going to bring me right back to 0. So that's a really good way to double check your shear diagram to make sure that it's right, is that all of your external forces cause you to jump back to 0 at the end. So now that I have my shear diagram, I can use that to find my moment diagram. Once again, I start at 0, but I have an external moment acting on my moment diagram. And so just like external forces cause jumps in my shear force diagram, external moments cause jumps in my moment diagram. And so here I have a clockwise moment. I found the value to be 153. Sorry, that's counterclockwise. I have a counterclockwise moment, and I found the value to be 153. Remember what I told you earlier about sign conventions that's really confusing about graphical method is that clockwise is positive and counterclockwise is negative. So because here I assumed that MA was counterclockwise and I found a positive value for it, when I use it here, I know that it's actually negative because I assumed counterclockwise and I assumed counterclockwise. I got a positive value. That tells me on my graphical method, my positive value here becomes a negative value here. So that gives me negative 153. So my external moment is going to cause me to jump from 0 to negative 153. And then from there, I know because I have a linear relationship with V, my M is going to be parabolic. Because the line is negative, I have a parabola that's curved down. So if you want to think about it this way, the slope is negative, so my parabola is sad. All right. Anyways, you'll notice that my parabola takes me to 0. Why do I know that? Well, I know that pins can't hold moments, and there's a pin at B, and there's nothing else that's happening other than this distributed load, which is causing the parabola. So I know that my parabola has to go from negative 153 to 0 because B can't hold a moment. So once I'm here at 0 again, I have a similar relationship to here where I had a line that became a slope. Here I have a line, and that's going to become a slope. In this case, my value 8 is above the x-axis, is positive. So I know that because my shear force is positive 8, my slope in my moment is going to be positive 8. So I'm going to increase until here, which is where the positive 8 ends. And I can figure out the change by taking the area under the curve. So if I have this here, I can calculate 8 times the 3 feet that it acts on. 8 times 3 is 24. So I know that my moment here at the end of that increase is 24. And then here you've got a negative 4 shear force, which is acting for the whole rest of the beam. So I know that I'm going to go from 24, I'm going to have a slope of negative 4, go all the way back down to 0. Because there's no moment acting on the end, I don't expect there to be a jump at the end. And so that's why it's a good check that my negative 4 here, my area, negative 4 times 6, also takes me back down to 0. So it's always good to check that your moment diagram starts and ends at 0. All right, we made our shear moment diagram. Very, very last steps. Basically, we can see from the moment diagram, the biggest absolute value number is 153. And so because of that, I can say my M max is 153. This is an instance where I'm taking the absolute value because I care about the maximum shear stress that's acting on the beam as a whole, not whether it's in tension or compression. So my M max is 153. This is in kip feet. Remember, units are really important. So I want to change that into kip inches because the standard for American units is PSI, pounds per square inch. So because that's in inches, I want to convert this into inches. So I'm multiplying by 12 to get my M max is equal to 1,836 kip inches. Now I'm going to plug that into my sigma bend equation, my over I. So coming back to this cross section we found earlier, I can assume my neutral axis is just down the middle because it is a symmetrical shape. And I know the equation for the for the moment of inertia of a rectangle is BH cubed over 12. I know B, I know H, I can calculate I. And then my Y is my distance from the neutral axis to the edge. Once again, because we're finding M max, the maximum value, because stress gets bigger as you go away from the neutral axis, my maximum value is going to be at the biggest distance I can get away from the neutral axis. So in this case, because this is 12 inches and my neutral axis is right in the middle, my y is going to be 6 inches. I'm going to take those values I know, plug them into this equation. Sigma is my over I. Make sure you're tracking your units throughout. So here I had m max in kip inches. So I took that value, I multiplied by 10 to the third to turn it into regular pounds, from kilopounds to regular pounds. Everything else was already in inches. And then I get at the end, sigma max is equal to 19.125 KSI. Once again, it's kind of a big number because it's a value for stress. I'm not too worried about it. And so that's a good way to verify that my number is at least in the right ballpark. Okay, so that's the last problem I have for you guys. I'm going to post these PDFs to the Canvas in addition to this video, just so you have a little bit more stuff to reference. And yeah, if you have any questions, you can always post them to Piazza. Unfortunately, the TAs don't actually have a lot of knowledge of, for example, how grading works, so I can't answer really those kinds of questions, but if you have technical questions, you can always go ahead and post those, or if I TA for a class that you're in, you can always ask those questions in chat during Zoom. And yeah, good luck everybody!